Hi everyone. Okay, the next thing that I want to go over before we construct the real numbers is we're just doing a couple of properties of real numbers, and then I'll get back to actually constructing them. The next thing is the density of the rationals in the real numbers. So the theorem is that if x is an element of R and y is an element of R and x is less than y, then there exists a p, a rational number, such that x is less than p is less than y. So in other words, for any two real numbers, there is a rational number between them. And if you think about that, it's very interesting. Last time I mentioned that there are infinitely more real numbers than there are rational numbers. And yet, nonetheless, there's somehow enough rational numbers to fit between all of the real numbers. So that's what we're going to prove here. And the way to phrase the way this is described is to say that rationals are dense in the reals. Okay, so one of the themes that is emerging from these videos is one of the things that I want us to do as we're working, building our knowledge, is we also need to get practice proving things generally and get better at doing that. And as I've said a couple times, part of the art, I think, of proving mathematical theorems is knowing what needs to be shown and what doesn't need to be shown. I've also said several times now, in math books, I think that 90% of the problem that you have understanding a math book comes from the author not making the proper judgment about what needs to be shown and what doesn't. So we've been following Walter Rudin's book for constructing the real numbers here. And so he proves this theorem. And I want to show you that he does exactly the thing that I'm talking about, where he makes this huge leap in logic that he simply does not justify at all. So first I'm just going to very quickly go through his proof, not explain it in any detail, but just to show you what the piece is that he does not justify. And then we're going to go through in detail and actually prove this theorem from scratch without leaving any gaps. His proof is that we're given that x is less than y. We're given that x is less than y. So we've seen before that means that y minus x is greater than 0, right? Because y is bigger than x, so if you subtract them, it's going to be bigger than 0. So the Archimedean property tells us that there's an integer n such that n times y minus x is greater than 1. This is just the Archimedean property, which says that if you have one number y and you have another number x, there's some integer where if you multiply the n times the x, it'll be bigger than y. Okay, so this is just a formulation of that, where 1 is y, y minus x is x, and then n. Okay, so if you distribute this, we have that ny minus nx is greater than 1. So if we use the Archimedean property again, we can find two positive integers, m1 and m2, such that m1 is greater than nx, and m2 is less than minus nx. Oh, this is the mistake I made here. Sorry, I screwed up here. Let's forget this. Let's do this on the next page. So we're at ny minus nx is greater than 1. So there's two positive integers, m1 and m2, such that we have that m1 is greater than nx, and we have that m2 is greater than minus nx. I had that as minus, as less than. So now if we flip the sign here, we have that minus m2 is less than nx, okay? So you put these together and you have minus m2 is less than nx is less than m1, okay? So now here's the part, so far so good, this is all fine. But then this is the claim that he makes. He says, thus there exists an integer m that's basically between m1 and m2, such that m minus 1 is less than or equal to nx is less than m. This is completely just unjustified. So what he's saying here is that above we found that if nx is here, there's some number over here, minus m2. There's some other number up here, m1. And that if this is the case, so these are integers and nx is between them, then there has to be an m in here somewhere such that m is just to the right of nx and m minus 1 is just to the left of nx. In other words, nx falls somewhere between two integers between this. Now, if you think about it, you can see that that's definitely true because the nx has to be in there somewhere. But this is completely unjustified from anything that we've learned so far. We've learned nothing about the natural numbers or the integers that would allow us to say this. But Rudin just decided not to bother with this and just to say, well, you can see that that's true, but I don't want to do that. And if we just use a little more, if we just build a little more, then we won't have to be jumping to any conclusions at all. And again, it's good practice to do these proofs anyway, and it helps your intuition to see how these things are built. So that's what we're going to do. I'm going to prove, and then from here, we're going to stop right here, but then the next step we'll get to after we justify this. So to do the actual proof of density of rationals inside the real numbers without any leaps in logic, we need to establish what is called the well-ordering of the natural numbers. It's very interesting because that concept that there's going to be two integers with the real number in between them is, again, that's something that we need to understand the natural numbers more before we can really prove that that's true. So the first thing is there's a concept that we're going to need for this, which is maximal number and a minimal number of a set. So the definition, suppose a set A is a subset of the real numbers. So A is a set of real numbers. A maximal element of A is a number M, which we write as max A, such that M is an element of A. and m is greater than or equal to x for every x in A. This should look very familiar because it sounds just like the supermum. But the important thing to understand is there's one big difference between this number and the supermum. The maximal number must be in the set, whereas the supermum does not have to be in the set. So as an example, you can just have a set of n element of R such that n is less than 0, right? So all the rational numbers, I should make that x, all the real numbers less than 0, this set has a supermum, which is 0. No number in this set is bigger than 0, but 0 is not actually in the set. But this set does not have a maximum because no matter how big, how close to 0 you get, you can always find one that's bigger. There's always a bigger number in this set. So the maximal number is not there, but the supermum is. Then just to complete these definitions, there's also a minimal, just like these. There's supermum and infimum. A minimal element of A is a number lowercase m equals min A, such that, again, m is, and the minimal is an element of A, and m is less than or equal to x for every x element of A. Okay? So it follows from this that if A has a maximal or minimal, then sup A equals max A, inf A equals min A. Okay, so if there is a maximal, then that number is going to be the supermum, but the set does not have to have a max while it does have to have a supermum. Okay, so now we need to write down what the actual nature of the natural numbers, which is that basically the natural numbers can be constructed by repeatedly adding 1. So you start with 1, and then the next one is 1 plus 1, then 1 plus 1 plus 1, 1 plus 1 plus 1, and so on. So about 100 years ago, a guy named Peano sort of did a formal analysis of natural numbers, and he came up with some axioms that will define the natural numbers. So again, this isn't something that we're proving. These are axioms, but we're positing this set with these properties and then call those the natural numbers, and then everything flows from there. And as we'll see when we do when we prove the uniqueness of the real numbers, all of the number systems stem from this. All of them are constructed from this simple thing. You start with 1, 1 plus 1, 1 plus 1 plus 1, then you start subtracting them from each other, and then you start dividing them, and then we use the least upper bound property, and then we have calculus. So there is a successor function sigma, lowercase sigma. So then these are the axioms, the Peano axioms, that define the natural numbers. 1, the number 1 is a natural number. 2, for every natural number, sigma n is a natural number. So you pick a natural number you're going to be able to apply the sigma to it. In other words, sigma is basically closed under the natural number. So every natural number has a number that's one bigger than it. And 3, sigma is injective, meaning we're also going to learn more about injective, surjective, and bijective when we do the uniqueness proof. For all m and n in the natural numbers, if m equals n, that implies that so that just means that, oh, this is if and only if, right? You can't have two natural numbers that succeed to the same number. Each natural number has one number that succeeds it. And then finally, there's one more, but for every natural number, n, sigma n equals 1 is false. What that means is there is no natural number whose successor is 1. Okay, so here's a little puzzle for you to consider. We've stated here that every natural number has a successor. But there's something missing here. We have not yet completely defined the natural numbers. Can you think why? So if you want to pause the video, do so and see if you can figure out what's missing here. And then I'll go ahead and answer it. So one of the whole reason that we're looking at this. So far we've said that every natural number has a successor, but this does not tell us that every natural number is the successor of some other number. So there could be some natural numbers sitting out there in space somewhere that aren't a part of this system. They just start out in the middle of nowhere and they have their successors, but it's independent of the chain starting at 1. So what we need to add to this is one last thing, the intuitive notion that every natural number can be obtained by applying sigma over and over to 1. So everything we did here didn't actually say that, like, if you just pick a number 100, that you'll be able to get to 100 by starting at 1 and going to the successors over and over and over. It could be sitting out there on its own. So we need an additional axiom or an additional statement in order to make that, to finalize the structure of the natural numbers. This axiom is actually called, and I'll talk more about this in a second, the axiom of induction. So let me write it down and then we'll talk about it. 5. Suppose that there's a set A that's a subset of the naturals, that it's a set of natural numbers such that 1 is an element of A, and n being an element of A implies that n plus 1 is an element of A. Then A equals the natural numbers. So what we said here, these two statements are just what we already have here, that 1 is a natural number and that for every natural number A, n plus 1 is also a natural number. But then the additional axiom is that then, if that is true, then A will equal the natural numbers. That A completes the natural numbers. There are no extra ones sitting out there anywhere. The interesting thing is that this defines the natural numbers. This is equivalent to the axiom of induction. So I'm not going to say anything more about this because already this is like really verging on being more logic than math, and I want to stick to the math side. So we're going to leave this where it is and move on with the math. But if you want, ask me in the comments and we can talk more about this and explore this more. So these are the natural numbers. Now, the well ordering property of natural numbers. Okay. Which is every non-empty subset of the natural numbers contains a minimal element. So this says every non-empty subset of the natural numbers contains a minimal element. Notice that it does not say it contains a maximal element, because you could say the set of all naturals, n greater than or equal to 5. So that's going to go up to infinity. There's no maximal element here, but there's definitely a minimal element, which would be 5. So the well-ordering property says that any set of natural numbers has a minimal element, does not need to have a maximal element. And the proof. So let's let S be a subset of the natural numbers. And let another set, A, be a set of natural numbers, which are 1, 2, 3, as long as they're not in S. So what this means is A is a consecutive set of natural numbers starting at 1 and ending before we hit a number in S. Okay, so S, this doesn't mean that S isn't necessarily everything else. Like S could be a set 5, 7, 9. So A would then be 1, 2, 3, 4. Okay, it's not going to have 6 and 8. It's just the consecutive ones below the first number in S. So the whole point of this proof, what we're going to see, is that either A is going to go on forever, or S is going to have a minimal element. That's how we're going to prove this. So we're going to use induction for the first time right now. The thing we just showed. To show that if S contains no minimal element, then S is the empty set. So this is an interesting set because this is an interesting proof because we're going to use both induction and then also we're proceeding with this proof by assuming the opposite. Remember, what we're trying to prove is that if S is a subset of natural numbers, then it will have a minimal element. So we're going to start by assuming that it does not, and then we're going to proceed by induction to show that S must be empty if it has no minimal element. So the way induction is done goes along exactly with this, with what we just described here. You start with an initial case, and then you assume n, and then you show that if n is true, then n plus 1 has to be true. And then that means that it has to be true for every step of the way. So the way you do a proof by induction, the initial step so we're going to start by proving that it's true for 1. So if 1 is not an element of A, then 1 is an element of S, right? So 1 is the then 1 is the minimal element of S because 1 is less than or equal to n for every n. Right? So if 1 is an element of S, then it has to be the minimal element. There's nothing smaller than 1 that could be in S. So that means that in this case, S does have a minimal element, but we assumed that S has no minimal element. So that means that 1 can't be in S. But if 1 is not in S, then 1 has to be an element of A. So we even sort of reached sort of a contradiction here because we said that let's start by saying that 1 is not an element of A. Then 1 has to be an element of S. But if 1 is an element of S, then 1 is the minimal element of S. That means that S has a minimal element. But we started by saying that S does not have a minimal element. That means that 1 can't be an S. That means that 1 has to be an A. So we've shown that the set A has to at least have 1. So now the induction step. So we've shown that at least the number 1 has to be an A. So now, and for any n in A, then n plus 1 has to also be an A. That is the induction step. So suppose that n is an element of A, meaning that if n is in A, what that means is that 1, 2, 3, up to n are all not in S, right? Because A is the set of the consecutive numbers from 1 up to some number that are not in S. So if n is in A, then at least this many are not in S. So what we want to know is, we're assuming that n is an element of A. What about n plus 1? Let's imagine that n plus 1 is not in A, which means n plus 1 is an element of S. That means that n plus 1 is the minimal element of S. right? Because we started with that n is not in S. So if n is not in S, but n plus 1 is in S, it has to be the minimal element because there's nothing smaller than it in S, because everything else is in A. So that means that n plus 1 is the minimal. That means that S has a minimal. Now we do the same thing that we did here. If n plus 1 is the minimal element of S, then we've contradicted our assumption, which was that S has no minimal element. That means that n plus 1 cannot be in S, which means that n plus 1 must be in A. So what we've shown here is that if n is in A, then n plus 1 must also be in A. That includes 1, because if we take n equals 1, then that means that 2 is in A. That means that 3 is in A, and so on. So we just showed that everything has to be in A. So what we've just shown is that if S has no minimal element, then A contains all natural numbers. That means that S is empty. So if S has anything in it, it has to have a minimal element. Okay. So the interesting thing here is that induction is considered to be an axiom of mathematics. And we used induction in order to prove the well-ordering of the natural numbers. But you can do it the other way around. You can actually assume the well-ordering of the natural numbers and use that to prove that that you can prove things by induction, that if it's true of n, it has to be true of n plus 1. So that in some way, the well-ordering property of the natural numbers is equivalent to the axiom of induction. So you can either assume induction and prove well-ordering, or you can assume that the natural numbers are well-ordered, in which case you can conclude from there that induction works. And all of this is necessary, all of this is assumed without being stated by Rudin. Okay, that's the well-ordering of the natural numbers. With this in hand, we'll be able to prove the density of the rationals in the next video. Thank you.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.